Okay, good morning again. Let's start, but let's see if others will join us in the middle of the discussion. So let's just review what we did last time. We started the module number 9, and we developed another way of creating integration quadrature formula. So sabi natin, yung mga quadratures, pang-approximate sila ng mga integrals, and then they take the form of this. So we replace the integral by simply taking linear combinations of um, the function values times some weights w sub I going from um, 0 to n or starting from 1 to n. It's just the indexing, so you can change it. All right, so ibig sabihin naghahanap tayo ng weights at saka abscisses na gagamitin. And then when we take this summation, we should get a good approximation to the integral. So we last time we look at or during the previous module we talked about the Newton cotes quadratures. Sabi natin may advantage yung Newton cotes kasi it doesn't matter what the exabytes we use. Um, okay lang siya. Mag-work yung yung Newton cotes quadrature formulas. And then the weights associated with it would be the integrals of the Lagrange basis polynomial. And then ibig sabihin, ang idea lang pala doon ay pinapalitan natin yung integrand by the interpolating polynomial because polynomials are easier to integrate because and then their integrals are also polynomials, so function evaluation is not a big hassle, right? Well, last time we look at last meeting we look at another way of or another form of quadrature rules, and that's the Gaussian quadrature formulas. Now the Gaussian quadrature formulas is quite different from Newton codes because in Gaussian formulas, meron tayong specific na exabytes na ginagamit. We're choosing the exabytes optimally with respect to the degree of precision of the quadrature formula. When we say degree of precision, you can think of it as the number m, for which the quadrature rule will give us exact approximate for the integrals for all polynomials of degree m or less, pero magkakamali na siya sa isang polynomial of degree m plus 1. Okay? And we said that if you're using endpoints in the Gaussian quadrature formula, then it will bring about two n unknowns. Okay? Bakit two n unknowns? Kasi una yung mga abscissas kailangan nating computin. There would be n of them. And then for each of these abscissas, dapat meron pa tayong mga associated weights. So merong n na unknown abscissas, tapos may n unknown weights associated with them. So we will get a 2n, we will have 2n unknowns in our system. And then this quadrature formula using endpoints will give us 2n minus 1 degree of precision. All right. So, and then dun sa definition ng degree of precision, dito natin kinuha yung system of equation na kailangan nating isolve para makuha yung x sub i's at saka yung mga w sub i's. Because since we are trying to get a quadrature formula of degree of precision 2n minus 1, our quadrature rule should be able to integrate to give us the integral of the following functions exactly: the constant function 1, the linear function x, x squared, x cubed, until x to the power 2n minus 1. So ito yung mga polynomials na dapat niyang ma-integrate ng eksakto. Simula kay 1, which is degree 0, hanggang kay x to the power 2n minus 1, which is degree 2n minus 1. And if you count how many polynomials yung gusto nating i-integrate ng eksakto, though theoretically, dapat ma-integrate niya lahat ng mga infinitely many polynomials of degree 2n minus 1 or less. But thanks to the linearity of the integral operator, kailangan na lang natin siyang i-check sa 2n na mga polynomials na ito. So each of these 2n polynomials will give us an equation, possibly nonlinear, especially starting from x squared and so on. And then we have 2n unknowns, so we're going to get a 2n by 2n system, all right? And it's quite manageable for n equals 1, n equals 2, probably for n equals 3, it's still fine. However, imagine you want to use 30 points in your integration formula. You will have a 60 by 60 nonlinear system, and that's not a good thing. All right? Napakahirap mag-solve, at least symbolically, ng system of nonlinear equations. The as you have recalled last time, gumamit tayo ng isang symbolic solver. We used MATLAB. You could use Wolfram Alpha or Mathematica or any other computing software or app para mag-solve ng nonlinear system. Kasi yung mga numerical methods para mag-solve ng linear systems, which might be handy, especially for large n's, ay nasa Math 175 pa. So kaya ngayon medyo constrained tayo dun sa klase ng systems na kaya nating isolve. Sa MATLAB, nakita nyo madali lang yung pagsasolve ng nonlinear system. Kaya lang ang problema kapag ka masyado ng malaki yung value ni n. Mahihirapan na si MATLAB mag-compute ng solution kasi kapag ka symbolic calculations, napaka-expensive ng mga yan. Alright? Hindi katulad ng mga iterative schemes or iterative numerical schemes na medyo kailangan lang mabilis yung CPU mo at saka may enough memory yung computer mo, the iterative algorithm can run smoothly. All right. Now, during my PhD during my PhD studies, I came across this reference or this book by Abramovich and Segan. This is a handbook of mathematical functions. Okay, so and then nice enough, binigay niya yung closed form formula or nagbigay siya ng isang closed form algorithm kung paano makukuha yung mga abscissas para sa Gaussian quadrature rules. Possibly it is already known. Hindi ko lang siya na-encounter before I didn't even bother looking because parang nakontento ako dun sa pagsasolve ng nonlinear system. But probably last year I came across this book by Abramovich and saw na okay, meron palang iba pang paraan para makuha yung mga abscissas at saka yung mga weights para sa Gaussian quadrature rules. Okay? And interestingly, yung mga exabytes pala para dun sa Gaussian quadrature rule are precisely the roots of the degree n Legendre polynomials. Okay? So, kung matatandaan nyo from interpolation, okay, na meet natin yung Legendre polynomials, which are the polynomials that will give the roots of which are the optimal interpolation abscissas with respect to the L2 norm. Okay? So, yun pala, meron pa siyang isang magandang property na yung roots ni Legendre polynomial, sila yung mga abscissas na ginagamit sa Gaussian quadrature rules. Okay? Now, just a caveat here, Legendre polynomials are defined only on the interval -1 to 1. So, ibig sabihin, yung makukuha nating mga roots niya ay nandun sa -1 to 1, which might be very handy para dun sa integration sa interval -1 to 1. Pero kapag yung integral na gusto nating i-approximate ay over an interval other than -1 to 1, kailangan nating i-translate at i-scale yung mga roots ni Legendre polynomials. Pero we have seen it before na naman last time. Nakita na natin last time kung paano gagawin yung translation, alright? Para dun sa isa nating example for LN2. Okay. Now, the nice thing about this is hindi na pala natin kailangan computen yung or i-solve yung system of nonlinear equations, which might be very difficult, especially for very large orders. Kaya nga lang, ang papalit natin sa kanya ay yung pag-compute ng roots ng Legendre polynomial. And I think napakita natin last time, if you still have your codes that you use for Legendre interpolation, that will be extremely helpful kasi pwede nyo na lang kunin yung part ng code na nagko-compute ng roots ng degree n Legendre polynomial. Tapos kukunin mo yung roots, tapos yung weights. Ang maganda ay nabibigay na rin ng formula mula sa equation 9.1. You simply take 2 over 1 minus the abscissa squared times the derivative of the Legendre polynomial evaluated at x by quantity squared. So if you know the roots of the Legendre polynomial, then you will also be able to compute the associated abscissas. Okay, so for instance, okay, so punta tayo sa P1. Kung gagamit ka ng isang point, alright, nakita natin last time na makukuha natin ay yung midpoint rule, alright, mula sa pagde-derive using the definition based on the degree of precision, okay? Pero kung titingnan natin siya in this light, kung yung one-point Gaussian formula, ang exabytes niya dapat ay yung root ng degree 1 Legendre polynomial. But the degree 1 Legendre polynomial is this linear function x. Right? So pag in-equate ko yan kay 0, makukuha kong x sub I ay z0 lamang, which is the midpoint between -1 and 1. So remember yung degree, yung 1-point Gaussian formula, siya lamang yung midpoint rule. Dito sa Legendre polynomials, ang interval ay -1 to 1. So we expect the abscissa to be equal to 0. And true enough, it is. Kasi siya yung 0 ng degree 1 Legendre polynomial. And then if we will compute the weight associated with the Legendre polynomial, so sa midpoint formula, siya yung length ng interval. Okay? So let's see what we'll get kung gagamitin natin itong formula 9.1. So ang weight associated for the first abscissa would be 2 over 1 minus exabyte squared, but exabyte squared is 0, so that's going to be 1 times derivative of p evaluated at 0 squared. So CP ay linear. Ang derivative niya ay constant 1. 1 squared is 1. Okay. And this will give us 2. And indeed, that is the length of the interval -1 to 1. Okay. It seems this is working as it should. Okay. Now, tingnan natin yung para sa 2 points. Para sa 2 points, ang second, ang degree 2 Legendre polynomial, tingnan natin dito. Nandito sa baba yung recursion formula, okay, para sa Legendre polynomial. So an alternative way to derive the 2-point Gaussian quadrature formula that we derived last time ay paggamit ng roots ng degree 2 Legendre polynomial. So first we need to know what is P2, okay? But P2 can be computed recursively using P0 and P1 via this formula, okay? So that is, we'll have 2 times 2 minus 1 over 2. So that's going to be 3 halves x times the previous Legendre polynomial, which is x, minus 2 minus 1 all over 2. So that's going to be 1 half times the Legendre polynomial 2 steps back. And that's going to be 1. So we'll have this. And this guy is simply 3 halves x squared minus 1 half. And if we will look for its roots, okay, wait mo lang yan kay 0, multiply both sides by 2, we get 3x squared minus 1 equals 0. And then we'll have 3x squared equals 1, x squared equals 1/3, x equals plus or minus root of 1/3, which is the same value as we have before. All right? Tapos kung kukomputin natin yung weights lang naman ay equals sa 2 over 1 minus exabyte squared. So it's going to be, if I will square this guy, I'll just get 1/3. Okay. Times the derivative of P, yung derivative ni P2 ay equals, so ito si P2, ang derivative niya ay 3x. Okay. So that means I'll have P2 prime of x squared would be equal to 9x. 9x squared. If I plug in the abscissas, I'll get 1/3 here, 1/3 times 9, so that's going to be times 3. Okay. And then we'll simplify this. We'll get 2 over 2/3 times 3. That would be 2 over 2 equal to 1. So that means the abscissas for the 2-point Gaussian quadrature is plus or minus root of 1/3. And the weights associated to both of these abscissas is equal to 1. Okay? Tapos, kung matatandaan nyo, ito rin yung Gaussian quadrature formula na na-derive natin using the degree of precision definition. Okay? Now, if you want to get higher or Legendre polynomials of, if you want to get Gaussian quadrature formulas using more points, then probably it might be easier to use Legendre polynomials. Okay, and this striking connection between the Gaussian quadrature formulas and Legendre polynomials prompted some, and actually most mathematicians use this. They refer to these quadrature rules as the Gauss Legendre quadrature rules. So usually I think ito yung mas sikat na tawag, hindi lang Gaussian quadrature rules. So they call it the Gauss Legendre quadrature rules to remind us that the roots of the Legendre polynomials are actually the abscissas used in these quadrature rules. Okay. Now, if you will be patient enough either to solve a large nonlinear system or to deal with high-order Legendre polynomials, you will be able to construct something similar to table 9.1. Okay? So pinapakita dito yung mga abscissas at saka mga weights for various Gauss Legendre quadrature rules. So if you want to use 3 points, so yung 3 points na yun will give us 2 times 3 minus 1. So that will give us degree of precision 5. Okay? Yung mga abscissas na kailangan yung gamitin ay 0 at saka plus or minus root of 3/5. And then the weights associated to them are, kay 0, ang weight na gagamitin nyo ay 8/9. Kay plus or minus root of 3/5, ang gagamitin yung weights ay 5/9. So if you are integrating, or if you want to approximate an integral over the interval -1 to 1, so pwede nyo itong gamitin. So you'll have 8/9 f of 0 plus 5/9 f of root of 3/5 plus 5/9 f of negative root of 3/5. Okay, so ito yung pang-approximate natin using, or this is actually the 3-point Gaussian quadrature formula for an integral from -1 to 1. Okay, and as expected, as we increase the number of points, the abscissas and the weights associated with them looks crazier and crazier. Okay, so pakomplikado na sila ng pakomplikado. But the nice thing is we have this table up until 5. You can explore MATLAB. I think kay MATLAB merong paraan para makita yung abscissas at saka mga weights para sa isang Gaussian quadrature formula or Gauss Legendre formula of for large values of n. So merong one-line command para makita sila. Okay, but at least until here until n equals 5, we have the abscissas and the weights listed in table 9.1. Okay, so let's do a quick example. Example 9.3. This is the third time that we will approximate the value of ln2 using a quadrature formula. This time we'll be using the 5-point Gauss Legendre quadrature formula. Okay. So again, we know that ln2 is equal to the integral of 1 over c dc from 1 to 2. So we'll use the 5-point Gauss Legendre formula. Okay. Kaya lang, we need to be careful because the abscissas used in table 9.1 are all from the interval -1 to 1. So kailangan natin siyang i-translate kasi ang integration interval natin dito ay 1 to 2. But actually, we can take advantage of the change of variable that we have seen last time, translating an integral from 1 to 2 to an integral to -1 to 1, from -1 to 1. Okay? So review natin kung paano natin siya ginawa. All right? So again, ln2 is equal to this integral, but this integral is not on the interval -1 to 1, but rather on the interval 1 to 2. So if you recall, dun sa change of variable natin last time, an integral from a to b of f of x dx can be rewritten, or gamitin ko na yung c na variable, okay, dc, can be written as an integral from -1 to 1, but this time scaled by the length of the interval over 2. So magkakaroon kanya dyan ng b minus a over 2. And then instead of the integrand evaluated at the variable c, i-evaluate natin siya dito sa b minus a over 2 times x plus a plus b over 2 dx. All right? Ito yung nanggaling dun sa change of variable na ginawa natin last time when we let c to be equal to b minus a over 2x plus a plus b over 2. Nag-change of variables, parang substitution sa Math 36. Kaya natin nakuha itong formula na ito. Okay? So the integration from a to b is that now boils down to an integration from -1 to 1. Okay? Tapos yung nasa loob natin ay scaled roots. Yung mga x's ay mga values from -1 to 1. Okay? Pero dahil dun sa scaling factors, sa scaling factor and translating term, itong mga values na pina-plug in natin kay f actually ay mga values na nanggagaling sa interval AB. Okay, so ito yung nangyayaring translation and scaling which should be familiar to you kasi ito rin yung ginamit nating pang-translate ng roots ng Legendre polynomials sa Chebyshev polynomials para makuha yung interpolating polynomial over an arbitrary interval. Okay. Now, if we will apply this to ln2, okay, para sa integral na to, siguro intermediate step dito. Singat natin. So this is equal to b minus a. So that's going to be 2 minus 1 over 2 times the integral from -1 to 1 of f of 1/2 x plus 3/2 dx. Okay? So in-apply ko lang yung substitution dito. So we'll get the 1/2 as our scaling factor outside of the integral. And then the integrand now will be replaced by, will still be 1 over x, but this time evaluated at 1/2 x plus 3 over 2. So instead na 1 over c yan, yung c mapapalitan ng 1/2 x plus 3/2. So kaya yung denominator na bago na. Okay? And then we will apply the quadrature formula para dito sa function na to. Okay? And what we will plug in here are x's coming from -1 to 1. But we already know what the x's that we will be using. The integration abscissas are actually this. 0 plus or minus this guy and plus or minus this guy. All right? Ito yung mga exabytes na ginamit ko. 5-point Gaussian quadrature rule kasi yung sabing gamitin. So ito yung para sa 5. Tapos yung weights associated para kay 0 ay 128 over 225. Yung weight para sa dalawang numbers na ito ay parehas 322 plus 13 root 70 over 900. Tapos para sa dalawang roots na to, ito naman yung associated weights. Okay? Now, if you'll do those calculations, okay, so meron kang b minus a over 2 na nanggaling dito. Dapat 1/2 na pala to. Okay? Tapos, kukunin mo yung weights times function values at those exabytes that I mentioned, you will get this value. You will get 34997 over 5490. Okay? And actually, this is the best approximation so far that we have for ln2 because the relative error here is just a bit below 3.28 times 10 to the -8. If you remember, I think dun sa 2-point Gaussian formula, ang relative error natin ay 0.12%. So that's 0.001 2. So that's going to be 1, 2, 3. 1.2 times 10 to the -3. And here we have gained 5 orders of accuracy. So kasi yung relative error niya naging order 10 to the -8 na. Okay? And I think that's it. Do you guys have any questions about what we did today? Clarifications? Kasi tapos na yung lecture today. So, pwede pala nag-overtime na lang tayo last time, no? Natapos sana natin and we don't have to get up too early today. But yeah, do you have guys? Do you have any questions, guys? Okay, kumusta naman so far? I know patapos na yung SEM, so probably most of your classes naghahapit na, tinatapos na yung coverage ng courses, tapos nagbibigay na rin ng mga problem sets um, para matapos na yung SEM. As far as 174 is concerned, we only have two modules left. Module 10, which is about Romberg integration and improper integrals. And then module 11 would be Monte Carlo simulations. Okay. But yeah, we're almost done, and I think we'll have 1 week buffer for which you can do your problem set alone. So pwedeng di na tayo mag-meet sa last week. Gagawin nyo na lang yung problem set para sa 174. Uh, hmm, ano pa ba? And then the details for the project, I'll give it on the first week of December. Okay, para before we part for the Christmas break, you have already talked to your class prospective group mates para dun sa problem. I just don't remember kung may napag-agrihan na tayo ng number of members in a group, but I'll check the recordings of our first meeting para ma-fix natin yung guidelines. So I'll give the guidelines next week. And then the deadline would be during the finals week. Titingnan ko kung tutuloy natin yung may presentation or written report na lang. So pag-usapan natin siguro next time. What else? Yeah, I think that's it. Do you guys have any questions? Okay, so if you have none, then probably we can spend 5 to 10 more minutes talking about the exercise. Maganda pag marami tayong oras na natitira, no? We can talk about the lab exercise. So this would be for Monday. Okay. So let's look at the problem. So the first problem is to verify the abscissas and weights given in the last row of table 9.1. Okay. So tingnan natin kung tama yung binigay nung table 9.1. And we were told to do this by deriving the 5-point Gaussian quadrature rule using the same strategy used in the module to get the 2-point Gaussian quadrature rule. So this is referring to the to the solving of the 2n by 2n equation via formed by imposing that our quadrature rule be of degree of precision 2n minus 1. Okay? So, ganun yung gagawin nyo. So, pwede nyo siya gawin, okay, 5-point Gaussian yung ating dinederive. So, that means we will have 10 unknowns, 5 abscissas, 5 weights, and then these numbers will give us a degree of precision 2n minus 1. So it would be of degree of precision 9. So being a degree of precision 9 formula, so dapat kaya niyang i-integrate si 1, si x squared, hanggang kay x to the 9th exactly. All right? So computin niyo yung integral ni 1 from negative 1 to 1, integral ni x from negative 1 to 1, hanggang integral ni x to the 9th from negative 1 to 1. It will not be that difficult because alam na natin na kapag ka-add yung degree, tama ba? Pag-add, saka nagzi-zero yung integral from negative 1 to 1. So, that gives you only half of this. So, 10 ito. So, 5 lang yung kailangan nyo i-compute by hand. Actually, may formula na rin yata para sa integral ng x to the power n when n is even. So, you can take a look at it. And then, i-equate nyo lang siya dun sa quadrature formula that would have been derived using these polynomials, okay? So magkakaroon ka ng 10 equation. So dapat dun sa exercise sasabihin nyo na, okay, by looking at the degree of precision, or pwede nyo sabihin, since we want the degree of precision to be 9, the following equations must hold. Yung quadrature rule equals integral ni 1 from negative 1 to 1, tapos, and so on. So, sulat nyo dito yung 10 nonlinear equations. And then, pag nasulat nyo na yung 10 nonlinear equations, you can just say using a solver, we get the following solution. The following solution to the system. Okay? So hindi nyo siya kailangang gawin by hand. 10 by 10 yan. So hindi naman kami terorista na ipapasolve namin sa inyo by hand. Yung 10 by 10 nonlinear system na yan. So gumamit kayo ng solver. Find something online. Check if MATLAB can do that also for you kasi medyo malaki na to. 10 by 10 na yung system. I don't know if MATLAB can still give it in a timely manner. So, or hanap kayo ng solver. Mathematica will be a great one. Kasi designed para sa symbolic calculations yung Mathematica or Maple. Wolfram Alpha is also good. And then there are also some freewares in the net or online solvers for this. Tapos sabihin nyo lang na ito yung mga exabytes na nakuha natin or nakuha nyo. Tapos ito yung W sub i's na nakuha nyo. Okay? So, dapat pala 5 yan, no? Kasi 10 point yung formula, 5 points yung formula. Okay? And then you're done. Just check that these numbers are equal to the ones given in table 9.1. And indeed, here you have verified using a different method yung entries ng table 9.1. So table 9.1 kasi ginamit ko yung Legendre polynomial. So dito sa XOR, hindi kayo pwedeng gumamit ng Legendre polynomial kasi pinapa-verify nga yung entries ng 9.1. So gamitin niyo yung degree of precision definition ng quadrature formula. Okay? And then the second part is to use the rule that you just derived to estimate the integral of e to the x squared dx from 0 to 1. Okay? So of course, kailangan yung gawin yung translation trick kasi yung integration interval dito ay from 0 to 1. Okay? So hindi kayo nag-plug in dito ng x squared lamang. Alright? So ang i-plug in nyo dyan ay yung b minus a over 2 times x plus a plus b over 2, where the x's are the roots of or the numbers you find in the last entry of table 9.1. Okay? And I think you should be good. I think the exercise is pretty straightforward. So good luck, guys, sa paggawa ng exercise 5.2. So yeah, I think that's it. Unless you have questions, mga pahabol na queries. Okay, so if there are none, so let's call it a day. A little bit early today, but that's fine. Lagi naman tayong overtime. So thank you guys for coming today. Enjoy your weekend. Also holiday ng November 30th, so I hope you will find some time. Panira yung Monday, no? Kailangan yung pumasok ng Monday at mag-lab. Tapos super long weekend sana. But anyway, that's what it is. So yeah, thank you guys for coming. Enjoy the rest of the day. Enjoy the weekend. And let's see each other again on Wednesday. Bye, everyone.